Hello, I'm Kirk Chassaniol with Thermo Scientific. Today we're going to talk about combustion ion chromatography. Combustion ion chromatography is rapidly becoming a good technique for the analysis of halogens in a wide variety of matrices that don't necessarily dissolve in water. So fluoride, chloride, bromide, and sulfur, in the petrochemical and electronics industries. There are regulatory methods associated with the technique. ASTM has a method, the standard test method for total fluorine, chlorine, and sulfur in aromatic hydrocarbons, followed by pyrohydrolytic combustion. And there are two other UOP methods, as well as a standard within the country of Korea as well. Again, same technique, analysis of halogens using combustion ion chromatography. So today we're going to give you an overview of ion chromatography and some of the benefits of reagent-free ion chromatography and continuous suppression that we use with the combustion IC system. And then I'll hand it over to my colleague, Mark Manahan, to go through an overview of the AQF, the hardware, go through some of the various sample types. And then we're going to tell you about a new technique for enrichment of the sample for lower detection limits for critical applications. So the basic components of an ion chromatograph. We have a pump, we have some sort of eluent or mobile phase, we have some way to introduce the sample, and then the real value is the separation process, and that occurs on the analytical column. A key component for any ion chromatography system is the suppressor. Since we're using conductivity as our detector here, suppressor is an integral part of the detection technique. And I'll go into more detail about that in later slides. But as I said, suppression is the key to ion chromatography. Another key component of an ion chromatograph is the materials of construction. All of the wetted parts, the flow path of our eluent, as well as our samples and detector, are all constructed of PEEK. It's a polyether ether ketone, an inert material that's resistant to strong acids and bases. So this is kind of a depiction of an ion exchange mechanism. So our analyte of interest, in this case, in the diagram, it's chloride. Chloride has a certain affinity for the anion exchange sites on the resin material. And then chloride is displaced by the eluent ion. In this case, in most of our cases, we use hydroxide as the quote-unquote pusher ion in an IC separation. But you can also use mixtures of carbonate and bicarbonate, as well as tetraborate as well. So the chloride has a certain affinity for the ion exchange resin. The eluent ion is present at much higher concentrations. As the analytes move the length of the column, they all band together and come off as a peak. So the role of suppression. In this case, we're using a potassium hydroxide eluent. And those of you that do conductivity measurements routinely know that if I measured the conductivity of a potassium hydroxide solution, it would be very high. So a suppressor used in ion chromatography is essentially a cation exchange device. So in this diagram, I'm using an eluent consisting of sodium hydroxide. Sodium hydroxide is very conductive on its own. I separate my fluoride, chloride, and sulfate. As we enter the suppressor, the cation exchange, the sodium is exchanged for hydronium. So my highly conductive sodium hydroxide eluent all of a sudden becomes water through the suppression process. Not only that, but my analytes of interest are in the acid form, a more conductive form of the analytes as opposed to the salt form. So in the diagram, you see, if I were to position my conductivity cell just at the outlet of the column, I would get a very high total conductivity and very small peaks on top of that. So the suppressor is a diagram in the lower diagram, and it eliminates the background conductivity and enhances the signal of my analytes, all in a water background. There's advantages to using hydroxide eluents, and one of the primary advantages is the suppressor product is water. So here we see another benefit of using hydroxide eluents. In the top chromatogram, we're using a 9 millimolar carbonate solution. And so the suppressor product, when we use carbonate eluents, is carbonic acid. And so we see circled there a water dip. So then that's one of the drawbacks to using carbonate eluents. Since we are in a background of carbonic acid, we see a water dip, which can compromise our ability to quantitate fluoride. As you see, it elutes very closely to the water dip. Well, when I use hydroxide eluents, my suppressor product is water. So I don't see a decrease in conductivity as the water associated with the sample moves through the detector. Not only that, the overall total conductivity is much lower, and it gives me the ability to run gradients in ion chromatography, which we'll talk about in later slides. But the larger the sample that you inject, the larger your sample loop, the larger the water dip will be. So with large loop injections, hydroxide eluents are the preferred technique. So what we see here is a typical IC system, generic type of IC system. We use an eluent, in this case, a mixture of carbonate and bicarbonate. We have our separator column and so forth. And our suppressor, in this case, is operating in the chemical mode, in which case I deliver sulfuric acid to that suppressor. So that's my source of hydronium for the neutralization of my highly conductive eluent. And then here we see what we call a reagent-free IC system. Reagent-free ion chromatography has gained a wide acceptance in the marketplace in ion chromatography. Basically, all I have to do is supply water to my ion chromatography system. In this case, I'm feeding water to the electrolytic eluent generator, so that I'm generating high purity eluents. In this case, I'm generating high purity potassium hydroxide. I purify that eluent using the continuously regenerated trap column. Again, it scrubs it of any impurities that may be present in the eluent and so forth. And then I separate on the column, and then I employ my electrolytic suppressor, in which case I don't need sulfuric acid to regenerate it. It operates in the recycle mode of operation here. And note in this diagram, I have inserted the gas absorption module, a key component of the combustion IC system that Mark will discuss in later slides. So the benefits of continuous chemical and electrolytic suppression. Chemical suppression, I supply sulfuric acid. Electrolytic suppression, I rely on the electrolysis of water to produce my hydronium that I need for suppression. But in both cases, it's continuous. So that means there's no need for regenerant solutions, for offline regeneration of the suppressor. It's always delivered. Chemically regenerated suppressant operating in the chemical mode, again, continuous suppression requires no offline regeneration. Some of the drawbacks that we experienced with suppression was first invented over 30 years ago. So the form of suppression is continuous in both cases, and whether it's our source of hydronium is sulfuric acid or the electrolysis of water, it's still a continuous form of suppression. So continuous suppression allows me to have longer run times. I don't have to take the suppressor offline to be regenerated. It allows me to use stronger mobile phases and not worry about possibly exhausting my suppressor. Gradient elution, which is a nice technique to help resolve closely eluting species or speed up an analysis, is possible with continuous suppression. And again, it's easy to implement and easy to validate as well. So the first suppressors were essentially columns packed with cation exchange resin, and there are today variations of that and improvements, but you're still dealing with a finite capacity. So I'm limited to the run times before I could possibly exhaust it. If I've got multiple chambers containing this cation exchange resin, I may have differences in reproducibility if I'm not regenerating it properly. I can use strong eluents not only to aid in my separation, but also to help clean up my column, in case to prevent fouling. And then the old packed bed suppressors do require sulfuric acid for regeneration. So continuous suppression is essentially maintenance-free. I wanted to show you the technique that we use for matrix elimination. And this is what we'll be talking about when we talk about sample enrichment with the combustion IC. So this is a general technique that's widely used in the semiconductor industry for determination of ions and various solvents, various matrices that we may not necessarily want to inject onto our column. In this case, we fill a large loop with our sample. We have a pump, and it's designated in the diagram as carrier pump 2, that pushes that sample displaces that sample from the loop, the large loop, onto a concentrator column. It further washes away the matrix or enriches the sample. So this is a two-valve approach that we use to help us employ matrix elimination. As I said, it's a general technique regardless if it's coupled with a combustion sample preparation system. And lastly, I'd like to conclude by saying that this sample preparation technique, combustion IC, can be interfaced with virtually any of the Thermo Scientific ICS systems, from our flagship model, the 5000 plus, all the way down to our starter line, the ICS-900. We tend to position the ICS-2100 the most with the combustion sample preparation because it's a nice, user-friendly, just add water, low maintenance, gradient elution system. But as I said, we can interface it not only with standard flows, but also with capillary flows across the whole product line. And now I'd like to hand it over to Mark Manahan of COSA Zentar for the conclusion about the technique of combustion IC.
Thank you, Kirk. Okay, here we have some typical samples for combustion ion chromatography: petrochemical, gases and LPG, gasoline and diesel, pharmaceuticals. The ASTM approved method for combustion IC is D7359, which is a D16 for aromatics method for combustion IC. Okay, the features of combustion IC is we're automating the measurement of chlorine, fluorine, bromine, iodide, and sulfur in a single analysis, or just halogens in the general analysis. Replaces dangerous wick bulb, bar bond methods. It's fast, only about 12 minutes per sample once you get the first combustion finished. Fully automated system, can do both solid, liquids, and gases, and LPG, solid, liquid, and gases with one system. Okay, here is a diagram, or a basic block diagram of combustion IC chromatography. You have the sample introduction boat, then you have the furnace, the gas absorption unit that absorbs the byproducts of the combustion prior to injection on the IC, and then the IC itself, which can be the most popular model, which is ICS-2100, although any IC can be used from the Thermo Dionex line. This is an actual picture of a combustion ion chromatography system with the liquid auto sampler on the right. Underneath that is the sample boat. In the middle, you'll see the AQF-2100 furnace. Then to the left of that is the combustion, the GA210. And then to the right is an ICS-2100 using auto eluent generation or reagent-free IC. Here is the same system, but with our solid auto sampler that has a 40-position solid auto sampler, where you would weigh the samples into the boat. Each boat would then be picked up and put into the furnace, burned, the gas is caught, injected. The beauty of both of these systems is that after the initial burn, each run is the chromatogram time. So it'll be like a 12-minute run, but the first one will be a combination of the combustion of about maybe anywhere from 8 to 12 minutes plus the IC run. Now, ease of access is a key component of any analytical instrument. And as you can see with this picture, to inspect or replace the pyrolysis tube is extremely easy with the hinged furnace. You just open it up. You don't have to let the system completely cool down to look at the condition of your pyro tube. And if you want to replace it, it cools off much faster when you open everything up. On the old system, you only had a couple of positions where you could move the boat in for combustion. The new 2100, they've improved that where we have more steps and we can move at a very slow rate to ensure that we don't have any incomplete combustions. So you can optimize the combustion to the specific need of the sample. Okay, here's a detailed picture of the GA210, and on the left there is an ES210. So there's two ways you can calibrate combustion IC, either aqueous samples directly on the IC or through the furnace. The ES210 allows the automated calibration of 3 systems. The GA210 has got 4 things. You see the initial burette for adding the absorption solution, the absorbing tube to the right, then you have the drain pump, and then the injection valve on the top left. Here is the actual control panel, so you don't have to control the unit through the software. You can actually control it manually through the control panel, similar to the control screen on the ICS-2100. This allows for routine troubleshooting very easily without having to run the full system. Here are 3 of our typical sample introduction systems. On the top is the liquid auto sampler model ASC250L. On the bottom is the AS2240. You can see 50 means 50 position auto sampler, 40 means 40 sample boats. And on the bottom is our gas injector for LPG and gases, the model GI240. Here is a sequence showing the sequences of combustion and chromatography. You have the sample prep, the burn, and the injection. You can see from this diagram that the next burn occurs before the ion chromatogram is done. So the first analysis is the time it takes to burn the sample plus the ion chromatograph. Every other analysis is the time of the ion chromatography. Okay, now we're getting into some actual data. And here is, we ran 0.51, 2.5, and 5 ppm standards of fluoride, chloride, bromide, and sulfur. And as you can see on the right column underneath recovery, we're all between 98 and 103% recovery, which show excellent linearity and precision of the system. Here's an actual chromatogram. Everyone loves to see a chromatogram. On this particular one, we're using an AS11HC column, and you can see the peak size and resolution. Here's another one with a lower concentration. We're using a 200 microliter loop, and we're doing fluoride, chloride, and sulfate. And notice phosphate is being used as an internal standard. On the old AQF100, we needed phosphate to adjust for the final volume. The new 2100 with the optical sensor internal standard is not required. Okay, here's an overlap of several chromatograms on top of one another with a weight of polymer of about 50 milligrams. And you can see the repeatability here in real time, or each individual analysis at around 1,000 ppm. Again, give you an idea of the precision of the technique. Combustion IC is a powerful technique and has a variety of applications. Its strength is also its weakness. You can do halogens and sulfur in a wide variety of matrices, but sometimes those matrices provide challenges. If you're doing a low fluoride and high sulfur concentration, you need to add peroxide. The peroxide could interfere with the fluoride peak. Also, if you're doing something like a flame retardant, that's an organophosphate compound, you can't use phosphate as an internal standard. The 2100 would, by using the optical sensor that allows a fixed volume regardless of the sample matrix, doesn't require phosphate and eliminates that problem. Also, if you're doing a low fluoride in a high chloride concentration, you can't optimize it. Or high bromide and sulfur where the peroxide is required. We'll get to this a little bit further in the slide, but this is where pre-concentration or matrix elimination is a strong technique. Okay, other challenges are increasing the sensitivity. You're limited by sample injection. It's not a good idea to inject the 500 or 100 microliter loop on a conventional IC. Final concentration of anion on the column may not be optimized for all the anions that you're looking for. So you can solve this by increasing sample size, doing replicate analysis before sample injection. Neither approach addresses the prime problem, which is I have a signal-to-noise ratio issue. Okay, pre-concentration technique. One way to do this is to use a very large sample injection, but concentrate it onto a pre-concentration column prior to injection. There's 2 terms. One would be if you're trying to increase the signal, or the other, which is called pre-concentration. The other one is matrix elimination, where you're trying to eliminate the peroxide interference. Okay, we're going to show you some data on pre-concentration with a 2100. The equipment used is an AQF2100H with an ICS-2100 using reagent-free IC. an AS18 column and guard column, a 1 mil sample loop, which is a very large loop. We're using the pump, an ALP1 pump, with an AXP-MS metering pump and a trap column. Here is a diagram of the flow diagram for pre-concentration. You have 2 injection loops. The 1 injection loop takes the sample from the absorption tube and fills the 1 mil loop. And then the injection loop on the ICS-2100, where the trap column is, will push that 1 mil loop onto the trap column. And then when the valve fires, we counterflow with the eluent onto the separation column. Here's some pictures of the system. On the left is just your 1 mil loop. The bottom right is the AXP-MS pump. There's an actual picture of the 1 mil loop in the GA210, the trap column on the ICS-2100. Here's a picture of the entire system in our lab in Houston, where we do a lot of the application work. As you can see, on the left's the pump, in the middle is the ICS-2100. On the right is the GA210, and that you can see hanging between the 2 instruments is the ES210 that we discussed previously. Now, here's where you can see the beauty of pre-concentration. On the top and the bottom are 2 exact chromatograms of the same standard, one using a 1 mil pump, a 1 mil loop, and the other one using a 200 microliter loop. And if you look at the areas, you can see that we're getting roughly 5 times the area on the 1 mil loop versus the 200 microliter loop. Here is taking the similar data and overlaying it so you can see how the fluoride peak is much larger and more easily resolved with the pre-concentration technique instead of using a 200 microliter direct injection. Now here's a solvent blank, or an example of an extremely low concentration sample where pre-concentration will dramatically improve your sensitivity and your repeatability and precision. Calibration curves showing linearity. We have a fluoride, a chloride, and a sulfur calibration curve. And here's some actual data where you can see how the precision for these concentrations is excellent. For a 100 ppb standard, you have a precision or an RSD of 1.9% for fluoride, and the rest of the data looks outstanding in my opinion. Here's another replicate where we did 3 replicates is considered 1 result, and we ran 2 results on 2 different days. This is some data that was used to generate some AST and precision data, and again you can see that by using pre-concentration, the repeatability and precision is excellent. So the summary. Pre-concentration can be easily configured to past systems or any new system. And at concentration of 100 to 500 ppb, you're looking at an RSD of roughly 2% or less. Based upon the data we've generated so far, we believe that the MDL, or minimum detection limit, is going to be around 50 parts per billion for the sample. And the same system will remove peroxide interference on the fluoride peak if you're trying to measure sulfur and peroxide is required. Okay, here's the list of the hardware required to do pre-concentration. We always use the ICS-2100 because, quite frankly, I don't want to make Eluent, and all I have to do with this is add water. You need the auxiliary pump, you need the trap column, and you need the what do we got here? Trap column and the low pressure concentrator. Thank you very much for your time, and if you have any questions, contact Zentar, COSA Zentar at cosazentar.com or thermofisher.com if you have any additional questions.